So maybe this week we will announce another assignment, the second assignment. Actually, it has, many problems in it. It has the amount of things you have to do might be twice compared to the previous one. Okay, so we are kind of merging two assignments. So this is might be, you can think this is assignment 2 and 3. Those are merged. Anyways, there are a few more problems. And this week, maybe by Wednesday, it will be announced. And the duration might be about 1 month. Okay, but basically, it's if you do assignment 1 properly, maybe the assignment 2 might be not very difficult. It is about training the segmentation network or the pose estimation network using the PyTorch. So basically, it would be similar to previous assignment. And so we are learning the transformer architecture, right? And another important notice is maybe near the final term exam, maybe a few days before the final exam period, we will have the quiz 2, and that will cover all the materials we are learning, okay, including the RCNN and also the YOLO and also the transformer. Okay. And may include some of the things from the content before the midterm. Okay, we will also include that. Okay, and there will be just 2 quiz. So quiz 2 might be the last quiz. Any questions? Yeah. Yeah, it's also the open book, but electronic devices is not allowed. Okay, including the calculator. Okay. Any other questions? So we learned about the LSTM and the RNN first, and also we learned that the RNN suffers from the vanishing gradient effect. So later, the LSTM is proposed, but I mean this LSTM is still works in the sequential way, both for encoder and decoder side. But the transformer, its operation is somehow parallelizing and thinking of the dense relations between the input. So we call this mechanism as the attention mechanism. So we calculate all the relationship between the input and encode that as the feature after the encoder. But the decoder is working in the sequential way. Okay, so decoder is more like the LSTM, but still given some for it. I mean this kind of encoding is a decoding is operated in the autoregressive way. So after getting one output, we input that and do this process to output the second one. And using when after getting the second output, we input it again and do operation by for 3 input and output the third input like that. So we gradually use the output from the previous time steps output as the input to the next time steps to predict the next time steps output. So this is kind of the autoregressive way. And but I mean, this is kind of the non-sequential process. This is kind of the sequential process, but given this input, auto-regressive input, they calculate the dense relationship between the autoregressive inputs, and using their dense relationship, they predict the output one by one. So given this, let's say we are given this three input, which is autoregressive, then we have to calculate their dense relationship to output the third output. So that's the difference to the LSTM based one. Still, LSTM works sequentially. So if you want to predict, if you want to predict this, let's say we are given these three input and want to predict the third output. In here, the LSTM decoder is encoding the first input first and propagate some information about the first input and combine it with the second input, and also propagate this context and input the third input, and then output the third output. So somehow they are in each autoregressive step, they are working sequentially to encode the feature. But in transformer, this entire decoder seems like it's sequential, but given one autoregressive task, they parallelly decode the output for each autoregressive step. Okay, are you guys captured this difference? Okay. So, anyways, transformer it is kind of parallelly consider the relationship between the input, but LSTM they have to consider their have to encode the input information in the sequential manner. In that sense, somehow the transformer is working better than previous sequential model. So because they can capture whole input at the same time and no risk to lose the past information. So transformer in that sense is robust to the previous sequential method, and also it can process it parallelly. So I mean, that could be also be efficient, more efficient than the sequential models. And now I may have to introduce the real attention mechanism. Okay, so I didn't tell you about what is this attention mechanism is yet. So this is our input. So this is some word embedding. So let's say we are understanding what I word is, but the computer cannot understand this. Instead, they have to calculate some fixed dimensional feature for each word we are using. Okay, so in NLP domain, they have already some method that can map this word to the some floating values, kind of the vector. Okay, so we call that as the word embedding. So this is kind of the n-dimensional vector. You can understand that like that. And also we have to, because transformer is parallelly regard all the input. Okay, so in LSTMs, we input I first, and then input N next, and all next, and student next. Okay, so in this manner, the LSTM can distinguish the order of the word, but in transformer, we parallelly input the inputs. So we have to have some additional scheme to differentiate the input their orders. So normally we make this kind of positional encoding vector and add that to the word embedding. So this is what we usually do. Okay, this is the positional encoding. And what we do next is we have to, given one word embedding, we will somehow transform it first. So this is, you can see this weight. This is kind of the weight you see in this kind of linear layer. Okay, so using this kind of weight, you can multiply this weight to the word embedding and make some encoded feature for that word. Okay, so this you will use these three weight, and we will call the first one as the query, and the second one as the key, and the next one is the value, query key value. So I don't know why they named this, but I mean, they are indicating three different vectors that is transformed from the same word embedding. So we will multiply three different weight metrics, which corresponds to this in the linear layer. And we will transform the same word vector into three different vectors, feature vector, okay? And the thing we will do next is in previous slide, I mentioned that this is somehow the input to the transformer, and this was the IN of student, which is kind of the forward. And then I said to you, we will consider their dense relationships, okay? And that is actually happened here, okay? So we first multiply, we actually find the query key values for these four words, okay? We will first get the queries for these four words. Then let's say the query for student are 2-dimension, then we can get this dimensional arrays, okay? For each word, each four word, we have to calculate 2-dimensional vector, and that makes this kind of matrix. And also for the key, we will also get the key for four words, okay? And by multiplying these two matrices, we can get this type of 4x4 matrix, which kind of calculate the dense relationship between these four words. Okay, are you guys agreeing with this? So this actually multiplying these two metrics is similar to getting the dot product between this individual how to say, for given this I word query, if you get the similarity, if you multiply, apply the dot product between this query for I and key for forward, then you can get the first first column vector of this array. Okay, so for each dimension, you can get one floating value that measures their similarity. Okay, cosine similarity maybe. Okay, so if you product these two vectors, you can get, if their their norm is 1, then you can get their cosine similarity actually. So that producting is a way to getting the similarity between these two vectors. So actually you can get similarity for each product, okay? And then if you do dot product between M query and all other keys, then you can get the second column vector, second row vector. And also if you do the same thing for this A query and student query, you can get actually this 4x4 similarity matrix between the queries and the keys. Okay, are you guys following this? Okay, so this is actually somehow encoding the dense relationship between the inputs. Okay. And then after doing this, so if you do this, you can get this kind of dense similarity, okay? And you will apply the softmax, okay? Softmax, by applying the softmax, you can somehow normalize each row vector and make it to have the one. I mean, there's some of the rows as one. Okay, that I mean, if you apply softmax, we already learned about the softmax. Okay, for given arbitrary vector having values which is larger than one, this is kind of low response. If we apply the softmax on this low matrix, we will apply exponential for each entry, and then we will normalize them by summing them. Okay, so we can secure that each entry have the positive value, and at the same time their sum is one. So we can do the same for this similarity to secure each one have positive value and sum of each row vector as one. Okay, so somehow we are indeed getting some similarity between the four words. I mean, for each input. And then what we do after that is we multiply again the value matrix for each word. And then this is our final feature. And we will call this as the attention value. Okay. So somehow by doing this, what you will obtain is so this is indicating the feature for I, and how this is encoded is you will get some, I mean, for making this, you will multiply the, how to say, this is I am a student, their values. Okay, this is a value feature. And you will, for getting the final feature for the I, you will multiply this value feature with the semantic, this kind of affinity matrix between the input. And actually getting this I feature, you will multiply with these four value features, but with their similarity to the I word. So, I mean, so M, their value is contributed to this I feature, but their contribution is decided by the similarity between M and I, their feature similarity encoded in this affinity matrix. And also A, their value feature contribute to make this I's feature, but their contribution is decided by the affinity matrix between I and M, their similarity, okay, and so on. So this is making some similarity, calculating the dense similarity between the input, and finally you multiply that with the value feature to make the final feature vector. Okay, are you guys understanding this? So this is actually the attention mechanism I explained before, and indeed they are seeing all the dense information between the input. We somehow calculate their similarity between dense input, and we multiply the value feature to according to their weight, their similarity. Okay, that's the attention mechanism. Are you guys following this? Okay, and but 아이고. I cannot delete other text. But I think I have to repeat these things. I mean, the next thing you have to remind is not cross entropy, cross attention, and self attention mechanism. Okay, so the thing we just learned is the self attention mechanism. So we somehow have calculate the query and keys between the input and calculate their similarity, and then multiply with the value feature to get the final feature for each input. Okay, that's the attention. And I mentioned that in the encoder, we will apply the self-attention mechanism. So the key query values are all from the original input. Okay. I mean, from the same word, we will get 3 vector key query value. And also here, we will get the key query value and so on. And then we will densely calculate their relationship by multiplying with query and key between the input, and finally multiply the value feature. Okay, and we get the final features here. And the next thing we have to understand is the cross attention mechanism. Okay. But before that, I have to explain this figure. So here is this is also the same figure with this figure. So the same figure, same operations could be represented in the 2 ways. So, I mean, this is more, frequently maybe used in the literature, because this NIPS paper, they are drawing this figure, and after that, people are using this as the transformer architecture. But I mean, this is more intuitive to understand the transformer operation. So, but I mean, basically they are equivalent figure. And input, from the input sequence, you have to add some, make it convert it into the word embedding, and also you have to add some positional encoding. Okay, that's also represented here. And here there are 3 arrows, and they are denoting key query values. Okay, so basically you will maybe I have to delete maybe. Okay. So here, from the input, by adding positional encoding with the original sequential input, you can get the input to the attention mechanism. And this is indicating each arrows that is indicating the key query values. Okay, and using that, you can apply the attention mechanism. and then encode some feature and apply some feed-forward network, which is same as the linear layers. Okay, and you somehow transform the encoded feature and transfer it to the decoder. And also in the decoder side, you have some some initial tokens or have the autoregressive input. Okay, that's your output sequence, and then you also apply some positional encoding here, and then input it, and this is the self-attention mechanism again. But the next transformer, this is very important, and you can see their attention mechanism. The key query values are not from the same, same output. Okay, so here you can see that two of them are coming from the encoder output, and only one is coming from the previous output. So here, I'm not sure which values were which might be query key, maybe values. Maybe VK is from the encoder output, and query might be from the previous layer's output. And somehow you multiply these two to calculate the similarity between the encoder output feature and the previous decoder output, and then multiply the encoder feature, okay, to get the final feature here. Okay, are you guys following this? Okay, so this is because why they are called as the cross attention mechanism. I mean, these two blocks are using the same input as the key query value. So that's why they are called as the self-attention mechanism. But here, the second attention block in the decoder, they are somehow mixing the information from the encoder and each the features encoded from the input. Okay, so they are somehow mixing the information and getting the output. Okay, so cross attention mechanism is doing that, and so their key query values are from the two sources. Okay, not from the same source. So that's why they are called as the cross attention. And then we transform it with some linear layers and output the output for current stream. Okay, so this is the transformer architecture. Are you guys following this? But I mean, sometimes it's very hard to understand the operation of the transformer because decoder is somehow it operates in the autoregressive way. So seeing only this figure, it is hard to understand maybe, yeah. But don't forget about that. And another important thing happened in the transformer is multi-head attention. So I mentioned that this is showing the self-attention mechanism. So somehow this is key and query, and you are multiplying, applying some dot product and scaling, and sometimes optionally we can also apply some mask and apply the softmax. Somehow this is calculating the similarity between two input, and then you will multiply it with the value feature. This is the self-attention mechanism, the attention mechanism in general. But when we call it as the multi-head attention, it means we have multiple streams of this one self-attention, one attention mechanism, and we have multiple weight for each stream. So now we have I index for this weight vector, and it indicates that we have multiple weight for key query value. Okay, so given one input, we will transform it to multiple key query set, and then after that, we will concatenate them. Their key query values output. We will concatenate them and apply the one last weight to this concatenated output, and this would be the final output. Okay, so this is very simple, right? We will have multiple key query value, and we will apply multiple times to get the multiple attention output, and we will concat such multiple output and apply one layer, one linear layer to merge them into the fixed dimensional vector. And this is our final output in the multi-head attention. So, I mean, if you do this, there would be some randomness, okay, in this multi-head. And in practice, it will provide us better accuracy, okay? So that's why we do this multi-head attention. So here you can see originally this attention was called as multi-head attention, okay? So that's explained here. Maybe the multi-heads, there would be 5 to 10 multi-head we normally use, okay? So this is the transformer, okay? But transformer in natural language processing domain, okay? Because in natural language processing, the input is naturally the sequences of the word, okay? And to process it, we have to, process it in this way, okay? So the transformer is developed for that. But nowadays, this transformer architecture is frequently used in the computer vision domain and replacing actually the convolutional neural network, their operations. In many applications, people are saying that nowadays the transformer is showing the better performance than the CNN architectures. Okay, and this is early paper in this stream of works that try to replace the CNN towards the transformer. So this is called as Vision transformer. So we will normally call that as the VIT, okay? So VI is from this Vision and T from this transformer. And you can see the similar architecture of transformer here, right? But there is actually one difference to the standard transformer. You have to notice that here. You can see only the encoder of the transformer in this architecture, Vision transformer. Okay, actually in Vision transformer, there is no decoder. Because decoder, it operates in the sequential manner, but the Vision application, there is no sequence. Okay, so what they do is very simple actually. This is the transformer, their encoder. Okay, and we need some input anyway. Okay, this kind of, we will we normally call this as some tokens or input to the transformer. Anyways, if we input this, make some tokens for the transformer encoder, then it will map all the input using the attention mechanism to have just one fixed dimensional vector, and using MLP after that to infer some class probability. We can do this to achieve the image classification task. Okay, and the input looks like this. So given n by n image, we will make some grid and divide the images into some patches. If the images is n by n, we will get some d by d patches. And each patches looks like this, okay? Somehow we transform them by applying some linear layer, and also we can add some positional embedding by using their XY positions, okay? And anyways, make this kind of tokens. If we train the transformer encoder, then we can actually train the transformer towards the image classification task, okay? And yeah, this is also showing that embedded patches, okay? This might be the feature for each patch plus the positioner, the spatial encoding, okay? And applying some differentiable layers and apply multi-head attention. And after that, we can map the fixed dimensional vector outputted from here to the final class probability maybe. And also we can have L repetitive these blocks. We can have we can repeat these blocks L times maybe. So this is the vision transformer architecture. Okay. Very simple, right? And this is showing that showing you more about the exact formula. So one another thing is here you have to have one reserved tokens. Okay, so I mean basically here if you will get the same dimensional actually the output with the original input. So this is indicating that Q query somehow softmax and divide by some constant, and you will multiply that with the value feature. Okay, this is our final output in the transformer encoder. Okay, so the final output of the transformer would be same dimension with the value feature. Okay, are you agree with that? Okay, so but these value features are features for each patch. Okay, so that this output would be some improved feature from the outputted from the transformer encoder that somehow consider the context or relationship between patches. But we have another distinguished vector. We have to have another distinguished token that will encode somehow the probability for images about the classification probability. So we have to reserve one output for getting such information. So here we are expecting such classification information is accumulated in this vector rather than other output. That corresponds to each individual patch's input. rather than using that, we make another one output that can somehow encode the overall image's classification probability and map it to the class probability using another MLPs. So this is denoting that actually. So this is the N patches feature encoding, but we reserve one token for the classification probability. And then we also add the positional embedding and apply multiple differentiable layers. This is the local normalization maybe. And this is the multi-head self-attention layer. And this is added to similar to the residual connection. And this is MLP and residual connection, and apply final normalization to get the final output. This is, this formula is explaining actually these blocks. Okay, this is actually very simple. And another thing I have to teach maybe is this one. So when training the transformer architecture, when training the transformer architecture, the thing which is actually trained is this weight matrix. Okay, so we have to train, we will train some sector of the entire architecture to change the output of that architecture. And each architecture in CNN, for example, the filter coefficients for the convolutional layer, that was the parameter sector, right? In transformer, these metrics, which transforms the input to key query values, this weight, are the parameters we will learn. Okay, but in this attention mechanism, actually there's no parameter to learn. Okay, but these parameters are implicitly learned to make this representation better for the the subsequent loss functions. Okay. So using this kind of architecture, we can train the transformer and actually how to transform the input into the key query values. Those are trained, and also there are in between this encoder and decoder, there are also the MLPs, and also these MLPs are also trained. Okay, are you guys following this? And the next important thing you have to learn is the DETR architecture. So vision transformer, it is very simple, right? It is the architecture for image classification using the transformer, okay? But DETR, this is the transformer-based architecture for object detection. So this is the object detection pipeline. And we already learned that VIT, that is only having the encoder, right? But here in DETR, we have both encoder and also the decoder. Okay, so because object detection, that is more complicated than the image classification task, so we need a detector here. Okay, and this is kind of the simple figure for explaining the DETR. And actually, when you read this paper, ECCB20, end-to-end object detection with transformer, you can see this kind of architecture. And actually, they are using CNN as well, okay, for encoding this image into vector you actually use this CNN architecture as well. Okay, and then they use actually each dimension. I mean, this would be one-dimensional feature vector. But you will use each element of this vector as one input to the transformer architecture. So now the input to the transformer is not anymore the patch. It's not anymore the patch, but the each dimension of this feature vector is used as the input to the transformer encoder. And anyways, we will use both encoder and decoder from the transformer, and we will map it to some bounding box information plus class probability. Because this is the output format of the object detector, right? In object detector, we have to estimate both bounding box and also the class probability for that bounding box, okay? So we have to calculate this, and we have to normally estimate a few hundred bounding boxes and their corresponding class probability, okay? Are you guys following this? Okay. And this is how they apply the loss function is explained here. So this is the DETR architecture, but the difference is we will additionally use the decoder architecture compared to the image classification transformer architecture. And this is more complicated figure for DETR. Okay. So using the CNN, given image I, we will first extract some feature, and we can encode some positional encoding, and by adding them, we constitute each token of the transformer encoder. Okay, and then we will somehow make the feature by encoding this image feature. Okay, we normally call this as the improved image feature. So CNN, it can already extract some image feature, right? But after that, transformer encoder, it improves its initial image feature, okay? And this part is similarly initialized to the, the NLP domain. So similarly, something is coming here, and that is cross-attended with the features obtained from the encoder, and we will get some feature anyways, and those are mapped to the class box with the corresponding label probability via this FFN, the feed-forward network, which might be the linear layer. Okay. And this is kind of those output. Okay. Are you guys following this? Okay. So overall, the pipeline looks very similar to the NLP transformer, right? But a very important difference lies here. Okay, so in NLP, I want to remind you of how transformer operate in the NLP domain. So we input some starting token here, and the first translated output comes out here, right? And then we input it in the autoregressive way as the second input, and also output, the second output. Somehow we sequentially did this in the NLP domain, right? But in the image domain, we don't have to do that because we already have all the pixels. Okay, we don't have to do that in the sequential way, and actually there is no order in the image pixels. Okay, we have to uniformly, or I mean, without orders, we have to parallelly input the pixels and have to infer their class probability and also the bounding box. Okay, so this decoder part is actually different from the transformers in the NLP domain. We actually input some vector that is describing maybe each region parallelly as the input to the transformer decoder. And we call this as the object queries. Here there's name already, okay? So we call this strange vector as the object query, okay? But thing is, there is actually no explicit meaning for this object query. But so in the NLP, this was the starting token or the previous decoding processes output, right? But in image domain, this is the meaningless vector that is trained to maximize the accuracy. I mean, these vectors are getting some gradient from the loss function, okay? So, I mean, to maximize the accuracy for these bounding boxes and class probability, you can get a gradient for these vectors. So these vectors are starting from the random vector, and they are trained to have some meaningless floating vector, but that can maximize the overall accuracy for this bounding box and class probability. Okay, so actually, initial DETR, there is no explicit meaning for these object queries, but later, people found that giving some spatial information for these object queries are helpful for accelerating the DETR training. So afterwards, people are improving this DETR in the aspect of that, but I mean, that's beyond of the scope of this lecture, so I will skip that. But in standard DETR, there is actually no meaning for these object queries, but these object queries are actually learned to have some meaning, maybe, but it's semantically no meaning, but it is trained to maximize the accuracy for this final output. Okay. And anyways, they are cross-attended with the initial feature and output, some output, intermediate output, which is mapped to the class probability and the image, the bounding boxes via these FFNs. Okay. So, and also object queries, they are normally over 300 object queries are, used because they are assuming that each object queries are mapped to each bounding box and class probability. So they are assuming that given one image, this amount of object will be inside. So that's what DETR is doing. Okay. And also, given these 300 object queries, they can be no object class. Okay. Most of them are becoming no object, and among them, some of them are mapped to real bounding box and class probability. Okay. So are you guys following this? This is actually very difficult. Okay. but I hope you can understand this because this will be increased. Okay. So actually, this is the transformer in the NLP domain. The left, that is the transformer in NLP domain. That actually operate somehow in the sequential manner for the decoder. Okay. But here you can see the decoder inputs are now the object queries. Okay. And they are one time inputted to the decoder, and there is no sequential step anymore. Okay. And this is the input to the encoder is now also the image feature rather than some sequential input. Okay. And without that, I mean, most of things are similar. So this is self-attention mechanism to improve, to get the improved image feature. Okay. And here for the object queries, you apply the self-attention and somehow you map it to some feature. And here you will use that as query and use the improved image feature as the VK and apply cross attention and map it to class probability and the bounding box. Okay, so this is the DETR architecture. The images are quite look similar, but you have to understand their difference. Okay. And actually, this is the last slide for the DETR. And when training this DETR, actually, we use two steps to train this DETR, but this is also very easy. Okay, so from the DETR, as I mentioned you, there are 300 sets of bounding box and class probability. Okay, I mean it depends the number of output. It depends on the number of object queries you set. Okay, so if you set object query number as 300, then you will get the same number of bounding box and the class probability. Okay. So this is kind of set of predictions. The bounding box and class, their set are here. But as I mentioned to you, most of them will be mapped to no object. Okay, only some of them will be mapped to real ground truth. Okay, and actually, the first step is filtering out among 300 predictions. You have to filter out when there is only two ground truths in that training sample. Then you have to filter out 298 98 sets of predictions. Okay, so you have to choose just two, which is best during the training. Okay, are you guys understanding this? So your predictions is the number of predictions from your DETR is 300, but if the ground truth image is having just if your ground truth is having just two ground truth objects, then you have to somehow filter out the bounding boxes which are far from the ground truth. Somehow you have to choose just two bounding box, which is the most closest to your ground truth. And the first step is doing that. Find the optimal prediction set. Among your prediction, you have to choose the best prediction of yours, which is closest to your ground truth. Okay. I mean, in the initial step, your output might not be like this, right? Of course, it would be completely random. But from the random prediction, you have to anyways find the predictions which are closest to your ground truth. Okay, that is the first step. Anyways, among 300 prediction, you have to choose maybe 2 if your number of ground truths is 2. Okay, you have to choose 2 predictions which is closest to your prediction. Okay, that's happened in this first step. And second, what you will do is you will actually apply loss function which closes your class prediction to the ground truth, and your bounding boxes close to your ground truth bounding box for 2 selected predictions. Okay, are you guys agreeing with that? I mean, if you try to apply these laws directly to your 300 predictions, then things will be very complicated and the training will not be converted easily. So you have to first select the best predictions among the whole predictions, and then apply the actual rules for that selected predictions only. Okay. So in DETR training, these 2 things are happening, and actually here that is explaining that. So you will, among all the configurations, so this is showing this sigma n. So if you are having n number of predictions, by shuffling them, you can make 300 factorial number of combination for that 300 predictions. Okay, but you have, and let's say this is ground truth, only having 2 ground truth boxes, and remaining boxes have to map to no object. Okay, so somehow, if you have this kind of combination for bounding boxes, then this is closest to the GT, but rest of them are not same. So I mean, among these 300 factorial combinations, this sigma hat would be the best match to the ground truth. So somehow you have to select the sigma hat that best match with the ground truth. Among all the combinations, you have to find the, this kind of sigma hat that best matches to your ground truth. That is sigma hat, and for that sigma hat, you will apply the actual loss. Okay, so I mean, this is formula explaining what I mentioned. Okay, but what actually happened during the training is choose selected predictions that best matches your ground truth. Among 300, you have to select 2 that best matches to your 2 ground truths. But if you have more than 2, then you can select more than 2. Okay. Anyways, that number is the number of ground truths, and then apply these rules to that selected predictions. Okay, and this is showing some result for the RCNN and DETR. So faster RCNN, that was the state of the art kind of, and you can get better accuracy actually using the DETR, which is the transformer-based object detection. So now this DETR is the state of the art, okay, in terms of accuracy. Okay, but YOLO is still best. I mean, showing the best trade-off between the speed and accuracy. But nowadays, this year, there appears real-time DETR, right? So some researchers are tuning this DETR to have both good accuracy and also the good speed. Okay, so we will also cover this real-time DETR maybe next class. I'm not sure, next week. maybe at least. Okay, so this is the end of today's lecture, and see you this Wednesday. Okay, thank you.